Hello everyone, Mr. Fawcett here, and we have another AP Calculus lesson for you. Today we're going to focus on the relationship between differentiability and continuity. So in Unit 1, we talked about what it meant for a function to be continuous at a specific point. And today we're going to talk about what it means for a function to be differentiable at a specific point. We've sort of talked about this in a more informal way. We drew some tangent lines on different graphs, and we discussed, well, can I draw a tangent line here? Are there multiple tangent lines that can be drawn to kind of get an idea of whether a function was differentiable? But now we're going to come up with a stringent definition for what it means for a function to be differentiable at a given point, just like we did with continuity. Okay, so we're going to build up to that. We're going to do a couple different examples and kind of put some thoughts together afterwards. So we're going to start off with number 1. And what you need to do is you can take out your graphing calculator, you can punch in that function f of x, and you just need to sketch it on the graph. Just a quick sketch will do. You don't have to have each point exact. Then you're going to think about part B, whether the function is continuous at x equals 2. Kind of explain your thinking. And then for part C, you're going to find the value of f prime of 2, so the derivative of f, and you're going to see whether or not the function is differentiable at x equals 2. Okay, so pause the video, take some time to answer those 3 questions, and then come on back. Okay, so hopefully you've graphed it in your calculator. I can pull up the TI-84 software just so you can see. So I've already entered it. If I hit graph, and we get something that looks like this. So on your calculator, it may look like it doesn't quite touch the x-axis here and here, but that's just the pixels on your calculator. If you think about this function, the square root of x squared minus 4, if I substitute in 2 and negative 2, that function is defined. I get 0 both times. So it does go all the way down. Let's get rid of these other 2 circles. It does go all the way down and touch the x-axis at negative 2 and positive 2. So we get a graph that looks like that. Now our second question was, is the function continuous at x equals 2? Well, we have to think about our definition of continuity, right? The function has to be defined, which it is. We have a point at x equals 2. The limit of the function as it approaches 2 has to exist. And we'll discuss that one because we may not get past this criteria. So the limit from the right side, right, as we approach 2 from this side, it's approaching 0. The problem is the function isn't defined from negative 2 to 2 on that open interval. So the limit as we approach 2 from the left side does not exist. There's no limit there. So the actual limit, as we look at the one-sided limits, they would have to be the same thing for the regular limit to exist. Because one of them is 0 and the other one is d and e, the limit does not exist, and we can just say, nope, the function is not continuous at x equals 2. So then I just wrote a reason. I said no, and then I gave the reason. If one of the one-sided limits does not exist, we know that the actual limit will not exist, so we can just say no, the function is not continuous. Okay, on to part C. It says find the value of f prime of 2 to determine if f of x is differentiable at x equals 2. Well, we talked about this in our last couple of lessons, or at least our last lesson. We can use our calculator to find a derivative. So let's get rid of this. And the way you do that, go to your home screen. Remember, I already have my function in at y1. Then I'm going to go to Math. I'm going to go down to option 8, and derive. My variable that I'm taking the derivative with respect to is x. For my function, you can either just type in the actual function, or remember, you can go to alpha trace and just click enter for y1, because that's where our function's entered. And we want to evaluate this at x equals 2. So we hit enter, and again, we don't get an answer. This is a calculator's way of telling us that the function is not differentiable at x equals 2. So this derivative value does not exist. There is no derivative value at x equals 2. Okay? So again, think about what this function looked like, right? It looked something like this. So it was not continuous at x equals 2, and it was not differentiable at x equals 2. All right, on to the next example. Same exact steps, just a different function. So pause the video, give me a sketch, and then talk about continuity and differentiability. All right, so if I go over here to my calculator, I've already typed in the function for us. I'm going to hit graph. And it's a little hard to tell from the graph. You may not exactly know what's going on right around x equals 0. But what's happening here is that there ends up being a vertical tangent. So when we draw it over here, we're going to get something that is a vertical tangent. Again, it's not, we'll do a little bit better job than that, but it's not as important how you draw it as long as you understand that there's a vertical tangent there. So let's think about it. Is the function continuous? Is the function defined at x equals 0? Well, it sure is. The y value there is 2. Does our function have a limit that exists at x equals 0? Right? So as I approach from both sides, is it approaching the same value? Well, it sure is, right? It's both one-sided limits are approaching 2 from the left and the right-hand side. So the first two criteria are met. The third criteria is that the value of the limit equals the value of the function. Let me just write that over here because that's a lot to say. So we need this to be true. The limit as x approaches 0 of f of x needs to be equal to f of 0. And we know that they are because we just said that the limit was equal to 2 and f of 0 was equal to 2. So our third criteria is good. The function is continuous. Okay, so the function was continuous. Let's now check its differentiability. So let's go back over here. I'm going to clear this for us. I'm going to go back to our calculator. Get to our home screen. Again, Math 8. Variable is x. Function is in y1. And we're evaluating at x equals 0. We click enter. And it tells us that the answer is 100. Now, if you think back to what I said about this graph, right, if we graph this, I did mention that there's a vertical tangent at x equals 0. So if there's a vertical tangent there, well, the derivative can't have a value of 100, right, because the value of the derivative at a vertical tangent, the slope of a vertical line, is undefined, right? It doesn't have a value. So something's going on with the calculator that is causing it to give us an incorrect answer. And while I don't know the exact inner workings of the calculator in this scenario, my knowledge of calculus, and hopefully your knowledge of calculus, should tell you that there's something wrong, right? If we look back at this original function, let me move this calculator over. If we just take the derivative real quick by hand, so we have f of x is equal to x to the power of 1/3 plus 2. If I take this derivative by hand, I'm going to get 1/3 times x to the power of negative 2/3. And if we write that with positive exponents and a radical, I'm going to get 1/3 times the cubed root of x squared. Now, if I substitute in 0 for x, if I take the derivative when x is equal to 0, I'm going to get 1/0, which is undefined. So when we actually show the work for finding the derivative, we know that the derivative is not defined at x equals 0. So regardless of what the calculator is telling us, we shouldn't just blindly take that calculator's answer. Sometimes, based on what the calculator has been programmed to do, when you do things that mathematically don't make sense, like divide by 0, sometimes the calculator can spit out values that just aren't true. Again, I don't know the inner workings of the calculator for this specific scenario, but what I do know is that the derivative should be undefined at this point. So having a good understanding of what this derivative looks like, so understanding that the derivative of this is going to have an x in the denominator, and then if I substitute in 0 for that x, I'm going to have a 0 in my denominator, and my derivative is going to be undefined. Having the knowledge of that can help you catch a mistake that the calculator is giving you, right? And the calculator isn't making a mistake when calculating the derivative because it's just doing what it's been programmed to do. But there's something fickle going on in the programming that doesn't spit out the value that we should get. We should get an error, or we should get something that is undefined. So when it says find the value of f prime of 0, that value is undefined. So not differentiable. And again, let's just take a real quick look again at what this graph looked like. Oops, let's get my eraser. So again, we had something that looked like this. So the function was continuous, but it had a vertical tangent at the point we were trying to take the derivative of, which made this function not differentiable at x equals 0. Okay, let's move on to the next example. So let's do the same process for this one. Sketch the graph from your calculator, figure out whether the function is continuous at x equals 0, and then try to figure out whether the function is differentiable at x equals 0. Again, assuming that you may need to double check the differentiability by taking the derivative by hand, just to be sure. Might be a good idea. Okay, so I'm going to pull up the calculator. Let's see what this function looks like. I already have it entered in my y1. I'm going to graph it. And I get a function that has a point or a cusp right at y equals 2. So if we begin to sketch that, it's coming down, and then it starts to spring back up at x equals 0. Okay. So is the function continuous at x equals 0? Well, it certainly looks continuous, but remember, we need to talk about the actual definition of continuity. So is the function defined? Well, f of 0, that's going to be equal to 2. And is the limit, or are the one-sided limits, the limit as x approaches 0 from the left-hand side of f of x, is that equal to the limit as x approaches 0 from the right-hand side or the positive side of f of x? Well, as we come in from the left-hand side, we're approaching 2. And as we come in from the right-hand side, we're also approaching 2. So again, this means that the actual limit, the limit as x approaches 0 of f of x, is equal to 2. And that is also equal to f of 0. So yes, the function is continuous. At x equals 0. So now we need to talk about differentiability. And before you just punch the function into the calculator and think about whether it's differentiable, let's think about what we know about differentiability. So likewise with limits, we've talked about a function being differentiable has to do with the slopes of the tangent lines. So can we draw a tangent line at x equals 0? Oops, didn't mean to erase all of that. Just want to get rid of that. Okay. So if I try to draw a tangent line, well, there is a point because the function's defined, but how do I know whether my tangent line should look... Oops. Let's go on my marker. How do I know if the tangent line should look like this or whether it should look like this? Those lines both are tangent to the function at x equals 0, but they have very different slopes, right? One is positive, one is negative. So how do I know which is right? Well, let's see what the calculator gives us, and then let's see what we get when we take the derivative by hand. So I'm going to clear. If we have to, we can sketch that function again. Okay, so let's go to my home screen. Remember, go to Math 8. Variables x, my function is in y1, and I'm taking it when x is equal to 0. And that spits me out a value of 0. So what this calculator is saying is that there's a horizontal tangent at the point x equals 0. Well, again, this graph is not a parabola. Right? A parabola would need to look something like this. So for the blue graph, there would be a horizontal tangent at x equals 2, but for the red graph, it's not clear why the tangent line would be horizontal, right? Why couldn't it have a positive or a negative slope? So let's do the derivative by hand and see if it can clear anything up for us. So f of x is equal to x to the 2/3 power plus 2. This is going to be a very similar derivative to our previous problem. So I get 2/3 times x to the power of negative 1/3. And if I convert that to positive exponents and then a radical, I end up getting 2 in my numerator and my denominator 3 times the cube root of x. And then if I substitute in 0 for x, I'm going to get 2 over 0, which is, again, it's undefined. And again, when you're looking at a graph and it's not very clear like what the tangent line should be, a lot of times it's going to be because it's undefined, because there isn't a clear tangent line. So the tangent line or the derivative value is not 0. It's not positive, it's not negative, it is undefined, which means that this function is not differentiable at x equals 0. Now you may say, Mr. Fawcett, do I always need to check the derivative by hand, right? Can I ever trust the calculator to give me the correct answer for the derivative? And the answer is no, you don't always need to check it by hand. But if you're unsure of whether the derivative is always going to be continuous, right? So if the derivative is defined at every single value, you don't have to worry about using the calculator. You can go right ahead and use it. But if you know that the derivative is going to be undefined at some spots, then it's probably a good idea to check your work by hand rather than just rely completely on the calculator. Because sometimes when there's math that you're not allowed to perform, like divide by 0, sometimes the calculator, the way it's programmed, can spit out an answer that is incorrect. So if you recognize that in the derivative there's going to be an x in the denominator or a variable in the denominator, and you're evaluating the derivative at 0, well, you may want to check the derivative by hand just to make sure that it's undefined rather than just rely on the calculator, because we've seen 2 examples here where the calculator has given us an incorrect answer. That being said, so we had a continuous function here, but again, it was not differentiable. So let's jump to the next page. Yeah, I think that was the last example. So it says, based on what you've seen, which is the true statement below? And then justify your reasoning on the lines below. So statement number 1, if a function is continuous, then it is differentiable. Number 2, if a function is differentiable, then it is continuous. And number 3 says both 1 and 2 are correct. So pick a statement you think is true and then try to justify it. And then we'll talk about what it specifically means for a function to be differentiable. Okay, so number 1 says if a function is continuous, then it is differentiable. But we specifically saw 2 examples, right? We had one that had a vertical tangent. That's a continuous function, but it is not differentiable at that vertical tangent, right? We saw another function that had a cusp. And again, that function is continuous, but it's not differentiable at that cusp. So number 1 is incorrect. And if number 1's incorrect or false, then number 3 has to be false because that says 1 and 2 are correct. So by process of elimination, we know that number 2 must be our true statement. So again, we're going to talk about why this is true, but for now, we're just going to put why the other ones weren't. So I think statement number 2 is correct because a function can be continuous but not differentiable. And again, those are strictly from our examples above that we tested. So if a function is differentiable, then it will be continuous, and we're going to talk about that right here. So for a function to be differentiable, then 2 things must be true. 1, it must be continuous. Now notice that that's not the only piece of criteria, right? Because we know that a function can be continuous, but it may not be differentiable. So this missing piece, this second piece of our definition, is that the limit as x approaches a from the negative side or from the left-hand side of the derivative, so f prime of x, must be equal to the limit as x approaches a from the positive side or the right-hand side of the derivative, so of f prime. I'm going to go down to the bottom. I'm going to go to a clean sheet and just show you what this means. We've already discussed this in terms of tangent lines, but you may not remember, and it's probably going to be a good refresher for you. So I'm going to get a clean sheet. Okay. So let's say I have a function. I'm just going to make this a standard parabola. And we'll call this x value a. So for f of x to be differentiable at a, right, it has to be continuous. And we can see from the graph that it is continuous. We could run through the 3 pieces of continuity, but we don't need to. We'll just go based off of how I drew it. Now, this part, where it says the limit as x approaches a from the left-hand side of f prime of x. So what that's saying is, what is the limit of the derivative, but what is the limit of the slopes of the tangent lines as we approach a? So as we approach a, right, we got a tangent line here. We can make another one. And we can make one more. What slope do those tangent lines seem to be approaching? Well, they seem to be approaching 0, right? We're eventually getting to that horizontal tangent. So we need to see if the same thing is happening on the right-hand side. So the limit as x approaches a from the right-hand side or the positive side of the derivative of f. So again, as we sketch out some tangent lines, we've got one that's negative and steep right there. We've got an, oops, that's poor. So we've got another negative one, but it's a little less steep. And then we've got one up here that's still negative, but again, less steep. So from both sides, the tangent lines are approaching the same slope, right? One is approaching, the purple tangent lines are all positive, but they're decreasing, so they're approaching 0. The green ones are all negative, but they're getting less and less negative as we approach this maximum. Because at the maximum, we have a horizontal tangent. So over here, these derivatives from both the left and the right-hand side are both approaching 0, which means that f of x is differentiable at x equals a. So as long as we know that f of x is continuous, which we already said was true, then we have to show that this equation right here is true. If this is true, then we can say f of x is differentiable at x equals a. But again, you also have to show that it's continuous, right? And again, you could go through the 3-part definition of continuity to show that. Okay, let me show you an example of when a function wouldn't be continuous, and we'll use one of the examples from up above. I don't need to erase all this actually, just some of it. Okay, so let's go with something like this. Okay, so as I approach x equals a from the left, my tangent lines start off negative, but they're not very negative, right? As I get closer and closer to that cusp, my tangent lines are getting more and more negative. So they're actually approaching, well, we don't know the exact number that they're approaching, but we just know that they're getting more and more negative. From the other side, I guess I should use green because that's what I wrote the other one in. From the other side, my tangent lines start off as positive, but not very positive, right? And then they get actually more and more positive as we approach that cusp. I know it's a little hard to see these tangent lines, but the tangent lines are approaching one set of tangent lines, the purple ones, are getting more and more negative. The other ones are getting more and more positive as you move towards x equals a. So they are not approaching the same value, which means that this statement is false, and thus f of x is not differentiable at x equals a. Okay? Okay. Let's see if we have anything else up there we need to do. But I think we have covered everything that we're going to cover in part 1. Yep, so in part 2, we'll pick up with some practice problems where we actually apply this definition of differentiability, as well as continue to review the definition of continuity, because for differentiability, you have to use continuity to prove it. So we're getting a review of Unit 1 as well. Okay, this is Mr. Fawcett. I hope you enjoy the rest of your day, and I look forward to seeing you for part 2.